Welcome back to our heat transfer class, where we are delving into the use of numerical methods for solving heat conduction problems within solids. This video was made with the support of InnoEnergy. After the introduction to the energy balance method, let us focus on the calculation of conductances. This lesson is divided into several parts. The energy balance method is based on dividing the medium into a sufficient number of volume elements, domains, or nodal regions, and then applying the energy conservation equation to each element. We start writing the conservation equation at a node. After that, we evaluate the internal heat generation, the heat inputs and outputs with neighboring nodes, and finally the stored energy. The result is a system of ordinary differential equations, as many as domains. The solution of the system of equations is the temperature distribution. In a steady state, it is a system of algebraic equations that can be solved easily. Conductances represent the description of the physical problem, including geometry, properties, and boundary conditions. Rectangular meshes. When the material is homogeneous and conductivity does not depend on the temperature, the conductance is calculated as the thermal conductivity multiplied by a cross-sectional area, when going from one node to the other, and divided by a distance or path. For the example in the figure, the cross-section is delta x times delta zeta and the path is delta y. When there is a change of material, we have to consider two resistances in series. The conductance will be the inverse of the sum of the two resistances in series. We can generalize for these cases writing paths and cross-sectional areas. Cylindrical coordinates. Given a cylinder, if there is temperature variation in the radial direction, r, we can divide the cylinder into domains that will be concentric cylindrical walls, except for the inner domain, which will remain a cylinder. If there is temperature variation in the direction of the axis, we can divide the cylinder into domains in the direction of zeta. If there is temperature variation in the direction of the angle, we can divide the cylinder into domains in the direction of the angle phi. The domains in cylindrical coordinates are segments of cylindrical walls, except the core domains, which are segments of a cylinder. The axial direction. Let us start with the axial direction, analyzing what are the cross-section and the path. The path is delta zeta, the distance between nodes in the axial direction. The cross-sectional area in the direction of heat conduction is an annulus fragment. Remember that if there is a change in thermal conductivity, you have to calculate two thermal resistances in series. Remember that the hypothesis of the energy balance methods is that conduction transfer occurs exclusively through lanes that are oriented in the direction of axes. Notice that in the angular direction, phi, heat goes from I to j through the arc. In this way, the cross-sectional area throughout the whole path is constant. This is the only case in which the path is not the distance. The path is the radius times the angle in radians. Remember that if there is a change in thermal conductivity, you have to calculate two thermal resistances in series. The radial direction. The cross-section is the arc multiplied by the height of the domain. However, the arc at I is different from the arc at j. This is the only case in which the cross-section when traveling from I to j is not constant. This is solved by taking the section halfway between I and j, which is known as the plane wall approximation. It is as if we had a flat wall, with a constant section, whose value is the average between the initial and final cross-sectional areas. Remember that if there is a change in thermal conductivity, you have to calculate two thermal resistances in series. Note that, for the plane wall approximation to be coherent, we do not change the cross-section, which remains the same. Being coherent means that if conductivities of I and J are the same, the equation for calculate the conductance must be the same as the one for constant conductivity. Mixed meshes. In meshes like the one shown in the figure where there is a change from rectangular mesh to a cylindrical mesh, the path between nodes is the sum of a straight path plus a path through the arc. The path from 1 to 2 is the sum of the straight path, B, and the path of the arc of radius A and angle pi8, which is half the delta phi. For the conductance 6 to 7, the calculation is similar, but the arch has a radius 3 times A. Convection conductances. The conductance between a solid node and a fluid with which it has contact on the surface is the result of putting two resistances in series, one for conduction inside the domain and another for convection in the outside area. If the conduction resistance is much lower than convection one, the overall conductance can be approximated by the product of the convection coefficient by the outer area, that is the area of the surface in contact with the fluid. As general rule, the conductance is the convection coefficient multiplied by the contact surface with the fluid. For a corner surface like the one shown in the figure for domain 6, to calculate the contact area of domain 6 with the outer fluid represented by node 10, we must add the area below and the side area. Radiation conductances. The radiation conductance with the surroundings can also be calculated. As general rule, the outer surface of the node exposed to the surroundings must be calculated. It is observed that this conductance depends on the temperature of the node surface. This fact forces to solve the system of equations iteratively when there are radiation conductances. Iterative problems. When conductances depend on node's temperature, it is necessary to assume initially a value of temperatures. The conductances are calculated using these values. With these conductances, the system of equations is solved to obtain new values of temperatures. With these new temperatures, conductances are calculated again. And so on until the calculation converges within a pre-established error.